So what we will be talking about today is the TV transmission. So we will discuss how when we watch our TVs, we have what we are watching. It's coming from the satellite, and the satellite they came from the station where they were filmed, or I don't know. Okay, we will focus on only the part from the satellite to our TVs. We'll only care about that. How does shows, images, videos come from the satellites to us? First, there will be two parts in the presentation. First, we will discuss what is used to send the information, because for it to come from the satellite to us, we need to send it in something. We'll talk about that. And then we will see that there is a little problem. So we will use a genius mathematical trick to solve the problem and enjoy watching TV. Okay, the thing we use to send the information from the satellite to us is electromagnetic waves. This is a very complicated technical term, so we will approach it by another example. Okay, the rope wave. Okay, this is something I did, and I'm sure most of you did as well. You can see here this blue dot. Okay, they represent a rope, so you can think of this as a rope. Now, if we make a perturbation at this point here, at point 0, let's see what will happen. Okay, here. The perturbation is moving. Well, I have done this many times as a child. I'm sure many of you did. Okay, simple. So let's analyze a little this thing. We have a rope. Perturbation in the rope that is moving along the rope. Simple enough. Now, these electromagnetic waves are something quite similar, but instead of a rope, there will be all of space. Okay, and of course the space between us and the satellite. And instead of a movement of a rope, there will be something else moving. This something else that will be moving, we can think of it as a force. So the satellites make a perturbation in space, and this perturbation is a kind of a force, and this force will be traveling along space the same way as this bump is moving along the rope. And when this perturbation reaches, it will be moving. Well, I said it's kind of a force. And when it moves across charges, like electrons or something like that, it applies a force on them. Okay? An example of that is, and I'm sure many of you have done it, if you are holding two magnets and you approach one of the magnets into the other, you can feel a force on the second magnet. This force is coming from the first one. So the first magnet is sending this force-like thing along space, and when it reaches the magnet, it applies a force on it, either pushing it away or pulling it. Okay? But in our case, it will be applied to charges, no magnets. But it's the same thing. And I will talk now about a situation that we have all experienced with these electromagnetic waves. Okay, imagine now this electromagnetic wave moving along space, and then it will reach some electrons. It will make them oscillate. These electrons are attached to some molecules, and these molecules will be in our eyes, and these molecules will send a signal to our brain, which will translate that into an image. Yes, these electromagnetic waves are light. So what we are seeing, like the light we see, what you are looking at your screens, the screen is making these perturbations in the space between you and the screen. This perturbation is moving along the space, and when it reaches your eyes, it will make some electrons in your eyes oscillate. Consequently, they will send a signal to your brain, and your brain will translate it into an image, and thus you are seeing me. Okay, let's see a little more how this lights will be behaving. Okay, here we can see it. Instead of a wave, instead of a bump, like we have seen in the case of the rope, it will be more continuous, as you can see. So it's a wavy thing. That's why we call it electromagnetic field wave, and electromagnetic because it has to do with electricity and magnetism. So this thing is moving through space and doing all those cool things. And the thing about color, it's just how elongated this wave is. For example, if we change this number here, okay, you can see that it's got a little contracted. Or if I do this, or this. So you can notice that the difference between these waves is how contracted or elongated they are. And this is what defines color. So when we talk about a blue color or red color, what we are actually talking about is how elongated or contracted it is. That's everything about light. Okay, so now when we are talking about satellites, it's doing the same thing. It's just sending some light that our eyes are not sensitive to. Our eyes cannot see that color. And as you know, there are infrared and ultraviolet. These are kinds of light that we cannot see because our eyes are not sensitive to that kind of light. And what the satellite is sending is radio waves. They are not, we cannot see them, but they are coming. So we have to use a satellite receiver that is sensitive to this kind of waves. It will receive them, and then it will translate them into some videos that we will see on our screens. The problem is the satellites we use for TV are so far away. The distance between the surface of the Earth and the satellite is around 35,000 kilometers. Can you imagine how enormous this distance is? Like we can put 3 Earths between us and the satellite. Like we have the surface of the Earth, we will put another Earth and another one and another one, and then we will reach the satellite. This is how far away it is. So the light, well, I will be calling it the light. The light coming from the satellite will be very dim. Imagine someone holding a candle and he is very far away from you. You will not be able to see the candle because he is far away, and the light will be distributed over a larger surface. So very little light will come to your eyes. This is the problem with the satellite. And the thing is, we cannot bring them closer, because if we do so, if we make them at a distance of, say, 20 kilometers, they will not be fixed in the sky. I think you have noticed that the satellites that are used for TV transmission, they are fixed in the sky. Like there is a certain direction that doesn't change. For example, the coming from them is really dim. We have to solve this problem. And to solve this problem, we will use some mathematical genius. Satellite dish, okay. Okay, this shape here is called a parabola. And I think it hints why we call it parabole. Okay. There is a squad of shapes in geometry that is called the conic sections, because they are conic sections. If we get a cone and make different sections in it, we'll get 4 kinds of shapes. These 4 are called conic sections. They are like the Ninja Turtles of geometry. And they have very interesting properties that they are used widely. And the thing we will need now is the parabola, and one of its really interesting properties. Okay, before we dive into that, I have to state 2 things. The first thing is metals are good reflectors of light. This is why they are shiny. Like metals are shiny because they reflect light. They are good reflectors. The second thing is the rays of light coming from the satellites, they come parallel to each other. Okay, and here is a little animation to justify why the rays coming from the satellites are parallel. Okay, we have here a source at the point 4, and as you can see, it's sending some rays. It's sending some rays everywhere, and you can see that they are not parallel, of course. Okay, now if you move a little the point, okay, let's move it. Let's take it away. Okay, it's changing it. It's at 24:30. You can see that the rays coming from it are becoming more and more parallel. Well, they are not exactly parallel, but they are becoming more and more parallel because it's far away. So when a source is far away, we can consider the rays coming from it as being parallel. And satellite, of course, is really far away, 35,000 kilometers. That's really much. And if we change its position vertically, you can say that you can see that the direction is coming, but still the rays are coming parallel. Okay, I guess this justifies why we consider the rays coming from the satellite to be parallel to each other. The satellite is really far away, and we can see it here how this happens. Okay, I will get it closer. When it gets far away, they get parallel. Okay, now using these two statements that metals are good reflectors of light and the rays coming from the satellites are parallel to each other, we will use a mathematical trick of this parabola here to solve the problem of the dim light. Okay, I will draw here a beam of light coming to the parabola. Okay, so here is the beam. It's coming vertically. It hits the surface of the parabola and it gets reflected. Well, that's why parabolas are made of metals. The satellite dish is made of metal. You don't see plastic satellite dishes because we need them to reflect light. And the rule that this reflection follows is that the angle here must be equal to the angle here. Okay, let's change now the ray coming. Okay, you can see here that the different rays are coming, different positions and different reflections. And if you can notice that all the rays are passing by this point here. You can see that no matter how I change the beam coming, the reflection always passes by this point. This is the interesting property of a parabola. A straight line coming vertically to the parabola will be reflected and always passes by this point that has a special name. It's called the foci, or the focus of the parabola. Now, well, of course, we have different rays coming from the satellite. They are everywhere, actually. So if we draw many of them, okay, I will have one at -1, -0.5, and another one at 1. Okay, we have here 5 rays, and you can see they are all coming here. Let me add a little more. Okay, you can see that all of them, they all pass by this point. They get focused here. That's why it's called the focal point, or the focus, or the foci, because all the rays reflected, they get focused into that point. And this is how we will solve the problem of the dim light coming from the satellite. We will use a parabolic surface of metal that will reflect all the rays and concentrate them at a single point, making the signal strong enough. Okay, I will talk about an example that you may be familiar with, the magnifying glass. You know, it's the thing that is like this, and people use it to magnify words and writing on a paper. Okay, you notice that well, I guess for the recording, sorry, I read the message and got distracted. Normal, it's recording. I don't know, we will check later. Okay, we got back to the magnifying glass. Maybe you have used it to use it in the sunlight to burn a bag or a paper or something. Well, of course, the rays coming from the sun, they are not enough to burn a paper or anything. But if we use the magnifying glass, well, the magnifying glass changes the direction of the rays coming. So we have parallel lines coming from the sun, and then they get focused into a single point, and we'll put a paper or a plastic bag or something into that spot where all the rays coming to the surface of the magnifying glass will be focused into a single point. And this way, the rays will be hot enough to burn something. This is the same principle used with the satellite dish. The only difference is that in a satellite dish, we are using reflection, but in the case of a magnifying glass, we are using refraction, which is the property of light that changes direction when it changes the medium. When it passes through glass, it will change direction. But it's the same principle. We are focusing rays to produce more energy at a single spot. It's the same principle. So this is the trick we use to solve that problem. And in this photo, the satellite receiver, we'll put it here. And this is why the satellite dishes are shaped like a parabola. And there is this thing where we put the satellite dish. That point is the focus of and that's it. That's the thing we use to solve the problem. Another thing we use this property and this shape for is in astronomy. Well, astronomical objects are really far away, like much further than any TV satellite is. We are talking about galaxies or nebulas or things like that. They are really far away. So what we do, we need to collect more light to see a clear image. So what we do is put a receiver in the focus of it. And there are really big ones. Well, the biggest one I know of is located in China. They are called radio telescopes. They are telescope shaped as a parabola to focus more light. And the biggest one that I know of, it's located in China. Its diameter is 500 meters. Like, imagine a parabolic dish of 500 meters. It's really giant. And it's used to focus radio waves coming from distant objects like pulsars, galaxies, nebulas. And we collect light to produce the images that we see. For example, the black hole that was pictured last year, I guess, used something similar, parabolic radio telescopes. Okay, that's it with parabolas. We will now move to another thing. Okay, I said earlier that they are four shapes, the conic sections, the Ninja Turtles of geometry. One of them is the parabola, and one of them is this shape you can see here in red. It's called an ellipse. And it's like a squished circle. So you get circle, you squish it in one direction, and you get an ellipse. It's one of those four famous shapes. And it has another reflective property. Okay, let's draw here some beams. Okay, we have here in blue a ray coming from this point here at 0, which, by the way, is one of the focuses, one of the foci. The ellipse has two foci. One of them is here. We have some ray coming from it. And we have a second foci somewhere else. Well, it's here at the point 4. This is the second foci of this ellipse. And we can see that if we change the ray, you can see that it always passes by the second focus. It's a similar reflexive property to the parabola. In the parabola, we have all rays coming from a distance far away will be focused in the foci. In the ellipse, all the rays coming from one foci will be focused on the other foci.
Oh, that's awesome.
It certainly is awesome. And there is a really awesome application that I will talk about in just a second. Okay, let me draw here some more some more rays. Okay, I will have this one minus 1 2. Okay, we have here some rays, and as you can see, all of them get focused there. So all of these rays, they come and get focused in this point here. Okay, now comes an amazing application of that. There are some things called whispering galleries. Okay, what are these? They are rooms that have the shape of an ellipse. So instead of a cubic room, we have a room whose walls are shaped like an ellipse. Okay, now you will stand at one of the foci, which is at 0 here, and another person will stand here at the point 4. We will assume that these are real dimensions, so he is 4 meters away from you. Okay, now you will whisper like this. Okay, that's why it's called whispering gallery. You will whisper, and all of the sound coming from your mouth will go in all directions, of course. It will get reflected on the walls, and all of your sound will be focused on this point that is 4 meters away from you. You know, the person there will hear you very clearly. Like, okay, we will put another person here, 0.5, so half a meter away from you. Let me draw that point. Okay, we have it at 0 and 0.5. No, 0. Wait, 0.5 and 0. Okay. Let's change his color. I choose blue. No, I will use that. Okay, orange. So we have a person standing here and another person standing here. Okay, and you are standing here at point 0. You will whisper. So you will make a very low voice, very low sound. Okay, now the voice will go in all directions. Okay, the voice will go in all of these directions, everywhere, and it will get reflected in the walls and travel again. So we have the ray coming straight in front will be heard by the person standing here. He will hear your voice because the sound coming from you will go to the front and reaches the person. He will hear you. The person that is standing here shouldn't be able as loudly as this person because he's very much far away. Okay, but the rays coming from this direction, this person will not hear it, but it will go, get reflected, and go to this person here. And every other sound that you produce, it will all be focused there. So this person here will hear you loudly than this person here. And if your voice is low enough, the person half a meter away from you will not be able to hear you, but the person who is 4 meters away from you will hear you like clearly. And this is really interesting. Okay, that is, there are many more applications for these shapes, the conic sections, and their reflective properties. Usually we use them to focus more rays, whether it's light waves or sound or anything. I chose these 2 examples to share with you because I find them really fascinating. Okay, this is the end of our presentation. And well, it wasn't long as the previous one. I told really a lot the last time. So we can discuss things if you want now, or if you have other questions. When we orient the satellite dish, we have to orient it toward the satellite. So we orient it toward the satellite so that the rays that come from the satellite will be perpendicular to the surface of
تما يجوا كيخبطوا في اسمه في البارابول يروحوا ديريكت لهذاك لي كابتي.
ايوه exactly.
هكاك تما هذاك هو البوان. هذاك هو البوان اللي تلقاو فيه.
هذاك البوان هو الفوصال تاع الساتلايت ديش.
واش اسمه هذاك دي كابتي؟
ساتلايت ريسيفر.
هذاك هو. تما هذاك هو اللي يحكم منه ويهبط لنا الصوره وكلش.
Yes.
بصح كيف
Eh
نخدموا
oui, on configure la tête.
بصح كيف يكابتي هذيك اسمه هذيك الاشعه اللي
Okay,
تجي
that's,
واش
that's the subject for
الكترون
another
داخل في
presentation.
الالكترونيك ولا كيفاه
Eh, électronique. Bon, راح نديرو un circuit اللي la fréquence de résonance تاعو هي la fréquence تاع les rayons électromagnétiques اللي راهم يجوا من الساتيليت. و بون حاجه كيما هكا. دونك لي ريون هذوك اللي راح يجوا راح يبوجيو دي زيليكترون في السيركوي هذاك، راح يعطونا ان سينيال الكتريك. ومن بعد السينيال الكتريك هذاك نديروا شويه بروسيسين ونرجعوا ايماج. Okay, we have here this parabola, and it has a property that lets it make all the rays come in vertically and reflected on its surface. It let them all focus in one single point. Let me draw them as they were. Minus 1.5 and minus 1. Okay, we have here some rays you can see, and they all get reflected on the surface and focused on this point. But as this shape, it collects all the rays coming from the satellite and focuses them here. وين نحطوا لا تيت؟ دونك لا تيت هذيك راح نحطوا فيها كاع لا lumière that the satellite dish will collect. ومن بعد it will be a strong signal. ولا تيت راح تقدر ترجعها ان كورون الكتريك. ومن بعد في الديمو راح يصرى بروسيسين واحد اخر باش يرجع هذاك لي سينال الكتريك يرجعوا ايماج. This is the main idea of the presentation. بون انا ديجا كتبت دوز ارتيكل على هذا لو سوجي، راهم في لاباج تاع فيزيكا. دونك في لاباج تاع فيزيكا حطوا تحت واقيلا مارس افريل هكا في هذيك لا بيريود مارس افريل. راه كاين دوز ارتيكل. الارتيكل الاول هدرت فيه على لا بارتي تاع الساتيليت كيفاش يبعث لي ريون الكترومagnétique. لا دوزيام بارتي هدرت على الساتلايت ديش وكيفاش it focuses the rays. دونك كاين صوالح راني كاتبهم في الارتيكل ما درتهمش هنا، كاين صوالح درتهم هنا ما درتهمش في الارتيكل. دونك if you are interested you can go and read it. Usually people are interested in the crazy ideas of physics like quantum mechanics, special and general theory of relativity. Well, they are amazing theories, they are very interesting, but I think that the most beautiful and elegant things they are the small things in objects that we see every day. And if we can really know them, like if we can know the principles upon which the everyday objects work, we will be really amazed. And maybe I will make other presentations about other things which are far more interesting than this satellite dish. I don't know. I will see if I later get the energy and the time to make other presentations. So that's it. Thank you for your attention and see you next time.